Hi, and welcome to clip number 5 in this Thermodynamics A2 series. And in previous clips, what we've done is we've looked at the Born-Haber cycles and we've generated unknown values within those cycles. But within each of the diagrams that we've looked at so far, the lattice enthalpy has been the largest step and arguably one of the most important steps in the Born-Haber cycle. That said, it's quite often an exam style question, and so what we're going to do is we're going to look at that lattice enthalpy value in a little bit more detail using 3 examples of ionic compounds. And we're going to look at, first of all, sodium chloride. We'll also look at sodium oxide, and then we'll also look at silver chloride. So NaCl would assume that we have an Na plus ion next door to a chloride ion. In a similar way, sodium oxide will have an Na plus ion next door to an oxide ion, O2 minus. Obviously, within the ratio of that compound, there would be 2 Na pluses next door to each O2 minus on a ratio, but for the purpose of this, we're looking at the lattice enthalpy association, lattice enthalpy value, which is the size of the electrostatic force of attraction between the 2 neighbouring ions. And so the fact that there's 2 of them doesn't really make much difference to the discussion that we're going to have here. And we have also this Ag plus, again, next door to a chloride ion, so a Cl minus ion. And what we've done there is we have, as we have seen at all stages through our chemistry career, we've assumed that we have perfectly spherical ions. And we're assuming that all of the interactions are happening in a perfect manner. We're assuming that there is no covalency between these ions. We're assuming that they are point charges and all of the things that we've assumed through GCSE about perfect ionic bonding. And so, looking at these values, we could get sodium chloride. Again, we would see some discrepancy sometimes depending on where you get your values from, but typically for sodium chloride we'd have a lattice enthalpy value of something in the region of 780 to 790 kilojoules per mole. Likewise for sodium oxide, something in the region of 2,500 ish, 2564 was the value I got there. And for silver chloride we'd have something again typically in the region of 760 kilojoules per mole. So this is assuming that everything is behaving perfectly ionically, and if we were to calculate the values from a Born-Haber cycle, we would get all of these theoretical values and we would calculate this value. However, what we see sometimes is that from the Born-Haber cycles, if we were to look at experimental values versus theoretical values, we would start to see some discrepancies sometimes. Sometimes large, sometimes small. And so for sodium chloride, you may expect to see values fairly similar to the 787 we've got here. Likewise, for sodium oxide, we would see values of typically 2,500. We're not going to see much discrepancy. However, if we were to look at silver chloride, we may see values quoted from Born-Haber cycles, which are using experimental data of around 905. Now there is a difference there, typically between 100 to 150 kilojoules per mole, again depending on where you get your values from. But what we're seeing there is a difference now between the theoretical value, the 760, assuming everything's perfect, and the real life experimental value of 905. This is due to the fact that silver chloride is not acting in a perfectly ionic fashion. It's not behaving where each of the ions are perfectly spherical. And what is possible is that we actually get, during the process of ionic bonding, we get a slight change from that perfect ionic model. So if we imagine that silver ion again next door to a chloride ion, if we remember, we have this negative ion with a cloud of electron charge density around it. And this is being pulled on by the silver plus metal cation. That is pulling at the electron charge sphere around the outside of the chloride ion. And what that's going to do is that's going to start to pull some of the electron charge into a non-spherical shape. It's going to distort this negative ion. And so as we get this distortion, what we actually now have is the existence of electron charge density forming between two non-metal ions. And when we get this situation whereby essentially we could simplify this to say that the silver and the chloride are now sharing some electrons, what we're starting to get is some covalent character. Now, this is not a full covalent bond. This is not like we would see in carbon dioxide or water or something like that. But we have seen the reverse of this, whereby we have had, in year one, we saw covalent character, which had, we had covalent bonds, which had ionic character. We were using those as dipole-dipole interactions. If you remember from earlier modules, we had dipole-dipole interactions whereby the covalent bonds became unsymmetrical and we got delta negative and delta positive ends on a covalent molecule. This is kind of the reverse of that. We've gone from an ionic system and we've introduced covalent character. This covalent character has now caused an additional bonding. And essentially, because we have an ionic lattice, a giant ionic lattice, we're kind of going towards a pseudo-giant covalent structure. Giant covalent structures are very, very strong, obviously, and so we get this additional bonding strength seen from theoretical values to real experimental values in the real world. Typically, as I say, the larger the difference between the two values that you're given, again, theoretical or experimental, the greater the amount of covalent character that a substance has. Sodium chloride, you will be given an experimental value and a theoretical value to the point where they're virtually the same, and so you can say that they are, to all intents and purposes, perfectly ionic. The ions are spherical and interacting in a purely electrostatic fashion. Likewise, sodium oxide would do similarly, but silver chloride is ionic but is displaying some covalent character. The good news is that whenever you see this covalent character, it always causes an increase in the lattice enthalpy value. It doesn't cause a decrease, so you would always see this increase in lattice enthalpy values, and so whenever you see that, it's always a good idea that what you're now seeing is the presence of this covalent character. And it's caused by the polarizing power of the silver ion. Silver ion is said to be polarizing towards the negative ion. So silver ions are highly polarizing, or are more polarizing than sodium ions. And so you get this tendency towards covalent character when either the metal ion, the positive ion, is small, or if the metal ion has a multiple charge. So if we were looking at aluminium, which is an Al3+, we would see a larger increase in the amount of covalent character in aluminium's ionic compounds. Likewise, if the chloride ion was replaced for a larger ion, such as bromide or iodide, then we could again get further distortion because the negative ion is increasing in its size and the attraction to its outer shell electrons by the nucleus is lower because of shielding and so on, as you saw in AS chemistry. So we get these differences, as we say, between the experimental values, which are typically larger than the theoretical values due to the presence of this covalent character, which is further caused by this distortion of the ion electron cloud around the negative ion. The closer the two values between theoretical and experimental, we can say that we are much more perfectly ionic. Now, one thing we didn't look at was just simply a comparison between the values. And what we saw in sodium chloride was a +1 versus a -1 charge. Likewise is the same as what we saw in the silver 1 to chloride 1 interaction, and both of those values were, give or take a little bit, within that kind of 700, 800, 900 kilojoules per mole region, and were something of that nature. What we've got here though is we've kept the sodium ion the same, so it's a sodium +1, but now when we've changed this, we've gone to an O2- ion. That has doubled the size of the charge on the oxide ion, or doubled the charge compared to the chloride ion, and so that electrostatic attraction is bigger. We've got attraction between a +1 species and a doubly minus oxide ion species here, and so we see an increase in the lattice enthalpy. You can't necessarily say that it will be double the size because it's related to the crystal structure and other such processes in the ionic lattice, but we can say that the greater the difference between the size of the positive metal ion and the size of the charge of the non-metal ion, so +1 to -1 or +2, +3 to -2, etc., then you'll get a larger lattice enthalpy. So if we swapped, again, for example, if we were to look at magnesium chloride, which is an Mg2+ versus a Cl-, again, we would expect to see that much larger than the sodium chloride in probably a similar ballpark, this time being 2+ to 1- as opposed to +1 to 2-. Again, we would see this, if we were to take an approximation, something in the region of 2,600 again, like we saw just above for sodium oxide. And so you can see that the size of the lattice enthalpy can change based on the charges of the ions in the ionic lattice, and it can also change in a slightly surprising way by this additional type of bonding, as we spoke about at the start of this clip, caused by distortion and this introduction of covalent character. Common exam questions there, as I said, quite useful in that the experimental values are always larger than the theoretical values because of the introduction of this top-up bonding of covalent character additional to the ionic we'd already seen. So the values for the experimental values are always larger. So have a look at some questions for those. Hopefully that will give you some clues as to answer those. Look at these questions alongside things such as periodicity, about sizes of ions and relationships between attraction of outer electrons and the nuclei, etc., etc. But, as I say, for thermodynamics in year 2, we've got this additional top-up of covalent character, and that's typically where the questions will lead you to in an exam. So thank you for listening on this one, and I will see you in the next one.